Our lesson today is on the greatest common factor. And similar to what we had done before, we are going to build upon your pre-existing skills. I know that in earlier classes, you've already seen how to get the greatest common factor of numbers. We are going to review that skill, and we'll do that skill both ways, whether you use the list method or you use the factor tree method. We'll go over both. But then we're also going to build upon that with some algebra and see how you would get the greatest common factor, not only of numbers, but the greatest common factor of monomials also. And so we'll start off with the definition of a common factor. Common factor is anything that will divide evenly into two or more terms. For example, 3 is a common factor of 12, 21, and 39. 3 will divide evenly into 12, it divides evenly into 21, and it divides evenly into 39. Therefore, it's a common factor of all of them. The greatest common factor we are going to define as kind of the biggest of all the possible common factors. And I'm putting down biggest. In terms of numbers, we could simply say it's actually the largest. 3 is greater than 1, so 3 is largest. When we start looking at monomials, the idea of biggest is going to be based on the exponents, and we'll see that coming up. Lastly, we have relatively prime. 2 things are called relatively prime when the greatest common factor is 1. That means they don't have anything in common except the number 1. And of course, everything has a common factor of 1 because 1 goes into absolutely everything. So informally, we would think of relatively prime as they don't have anything in common. Now, some examples of that. Let's say we have the number 5. 5 actually is a prime number. So I'm going to use 15. 15 has factors of 1, 3, 5, and 15. We've got a list of things that go into 15. If we take the number 16, 1, 2, 4, 8, and 16. If we start comparing the factors, what number appears on both lists? The number 1 appears on both lists, and that's it. They don't have anything else in common. 15 and 16 then are an example of relatively prime numbers. That's exactly what it is. The greatest common factor is 1. When that happens, we call them relatively prime. Now, if we took 5, and here I'm going to look at 5 and 15, they have the common factor of 1 also. But they also have a second common factor of 5. The fact that there's something in common bigger than 1 means these are not relatively prime. And we'll come back and look at these with a little bit more detail as well. Now, first thing we want to be able to do is find the greatest common factor. So here's our situation. A high school asks for volunteers to help clean up local highways one Saturday each month. The group has 27 freshman volunteers, 18 sophomores, 36 juniors, 45 seniors. What is the greatest, and I want to point that particular piece out, the fact that you're using the term greatest should be an indicator that you're searching for greatest common factor. What is the greatest number of groups that can be formed if every group has to have the same number of students, freshmen, sophomores, juniors, seniors. Basically then, we just want to know what is the greatest common factor of 27, 18, 36, and 45. In order to do that, we need to create the list of factors. Of course, in an earlier video, we've already practiced listing out the factors, so I'm going to go through that a little bit more quickly here. We saw that we have 1 times 27, 3 times 9, and that's it. 1 times 18, 2 times 9, 3 times 6, 1 times 36, 2 times 18, 3 times 12, 4 times 9, and 6 times 6. 1 times 45, 3 times 15, 5 times 9. And I know I went through those quickly. It's a pre-existing skill. You've already demonstrated that you can do this. So, what numbers appear on every single list? 1 appears on every list. It's there. We've got the common 1. There is a common 3. There is a common 9. And so we have common factors 1, 3, and 9. What is the greatest common factor? 9. We have 9. And this is one way to do it. We've identified the greatest common factor just by listing out everything that they all have in common. Now, there is a second way to find that greatest common factor of 9. And admittedly, from my experience, most students prefer to use the list method just because they're more comfortable with it. When you start working with larger numbers, though, the prime factorization method usually works better. And in fact, the prime factorization method is the one that we need to use when we're working with monomials. It's not really effective to start listing factors for monomials. We need to use this method once variables get involved. And it's based on prime factorization. Creating a factor tree, we need to create the list of prime factorizations. For instance, 27, after you do a factor tree, you would get 3 times 3 times 3. Progressing forward with 18, 18 is 2 times 3 times 3. 36, 2 times 3 times 2 times 3, because it's 6 times 6. 45 as 5 times 9, 3 times 3 times 5. To get that list, I did a factor tree in my head. I don't want to leave anyone behind. Is there any of these? Are there any of these that you want to see the factor tree and how we created them? Okay, so with these pieces, we had 27, and we could create our factor tree of 9 times 3. 3 is a prime number, so that one can stop. 27 as a composite number has to be split up again. That's another 3 times 3. After creating the factor tree and recognizing my prime numbers, it led me towards saying 27 is 3 times 3 times 3. Yes. Because I'm very experienced with these pieces, I don't personally need to write down the factor tree to create the prime factorization. I do it in my head. I know that most students don't have the ability to do that. Most students would need to draw out the factor tree and say, this is 3 times 6, and 2 times 3, leading them to the prime factorization, 2 times 3 times 3. As long as you can create the factor tree, you can create the list of prime factorizations. I will admit my personal preference is this method as opposed to the list method, in large part because I don't have to spend as much time writing. It's easier for me. Well, the next component that we have to do, we need to identify all the common primes. What number appears in every single prime factorization?
3.
There is a 3. And that 3 is occurring here, 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 and here. We have now used up those 3's in the yellow. Do you see any other numbers that appear on all 4 lists? Yes. We also have, and I'll use these in the greens, 3, 3, 3, and 3. There is another 3 on every single list. So we'll use that one. Is there anything else on all 4 lists? No. The only thing left for 45 is this 5, and that doesn't connect anywhere else. Yes, there are 2's that match up on these 2 lists, but there's no other number that appears on all 4. Well, after we've identified the common prime numbers, just multiply them. 3 times 3. Here's our greatest common factor. This tells us then that the largest number of groups that can be formed that will all be the same type is 9. 9 different groups. Well, when we take the 27 freshmen split up amongst 9 groups, how many freshmen are in each group? 27 divided by 9 gives us 3 freshmen per group. 18 sophomores split up amongst 9 groups would give us 2 sophomores per group. 36 divided by 9 gives us 4 juniors per group. And 45 divided by 9 gives us 5 seniors per group. Yes, it's a big group. So when we start, we were not asked to figure this out, but we could then say 3 freshmen, 2 sophomores, 3 plus 2 is 5, plus 4 juniors is 9, plus 5 seniors is 14. There will be a total of 14 people per group. We were not asked to get that information, but if we wanted to extend it further, we could. Now, picking whatever method you want, whether we do a list method or we do a factor tree method, prime factorization method. Let's get the greatest common factor. Right, so we're only going to do one, so please give me a quick show of hands. Who wants to do number 1? Who wants to do number 2? All right, so number 1 wins out. Are we going to use the list method or the factor tree method? Okay, choosing the factor tree method, and I don't want to use yellow, so we're going to start off by creating our factor tree for 54. What are 2 numbers that multiply to 54? 9 and 6. Split that up as 3 times 3 and 3 times 2. So 54 has the prime factorization 2 times 3 times 3 times 3. Now we need the factor tree for 81. 9 times 9, which both split up as 3 times 3. So 81 has prime factorization 3 times 3 times 3 times 3. Now that we have our prime factorizations, we need to identify what do they have in common. We've got a common 3, another common 3, so that will have to be multiplied, and another common 3, which needs to be multiplied. After grabbing each of the common pairs, 3 times 3 times 3 equals 27, and we have our answer. You, of course, have a choice. You can choose to do the list method. You can choose to do the factor tree method. Both of them are correct. Both of them are valid. Pick the way that you like to do it. I will tell you my personal preference. Small numbers, like something that's less than 30, I like to do lists because I can list them all out quickly. It's harder to create a list when you're working with numbers like 81 and 95, and sometimes it's just harder for people to visualize. When I start working with big numbers, I prefer to use the factor tree method. It's just what works better for my brain. You get to pick what's good for your brain and do it the way that you like. Both of them are good, both of them are valid. Just make sure that you know how to get the greatest common factor. Next, we need to identify relatively prime numbers. Relatively prime numbers have only the single common factor of 1. And so we could once again do this 2 different ways. We can do it by creating a list of factors. We could also do it with prime factorization. We'll see how to do it both ways. Then you can pick the way that you like to do it. So, what are the list of factors for 28? 1 times 28, 2 times 14, 4 times 7, and we've got it. We also need the factors of 63. 1 times 63, 3 times 31, I'm sorry, 21, not 31. Then we had 7 times 9. So we've created our list of factors. What is the largest number on both lists? The largest number common to both lists. They both have a factor of 7 involved. They both have a factor of 1. But the largest common factor, the greatest common factor, is 7. Because the GCF is not 1, it is not relatively prime. Okay, there's no verb there. The numbers are not relatively prime. Using the prime factorization method for part B, 42 we know is 6 times 7. And so we wind up with 42 is 2 times 3 times 7. 55 is nothing more than 5 times 11. What we've done is create the prime factorization for both numbers. And now we're looking to see what they have in common. What number appears on both prime factorization lists? Nothing. Nothing is in common for 42 and 55 with their prime factorizations. When there's nothing in common, the greatest common factor is 1. Because the greatest common factor is 1, the numbers are relatively prime. All right, so once again, let's choose one. And since you're doing these on your marker board, you pick which one you want to do. I'll pause the video while you've got some time to work. Now, what I'm noticing, I'm seeing a lot of people trying out the factor tree method, completely valid. But this is a big reason why I like the list method. When I start listing out my factors of 49, the only ones are 1, 7, and 49. There are only 3 things that go into it. Will 49 go inside 30?
No.
No. Will 7 fit inside 30 perfectly? No. Well, if neither one of those are factors of 30, then I don't have to do anything else. I already know that the greatest common factor has to be 1 because the other two possibilities don't work. Because my greatest common factor is 1, I know that these actually are relatively prime. That's a big reason why I like the list method better. Also, when I look over at 4, I don't need the full prime factorization. Can you tell me any number that's going to divide into both of those?
1.
How about 2? They're both even numbers. If they're both even numbers, we've got a factor that's bigger than 1. I don't even need to know what their greatest common factor is. There's something bigger than 1. Immediately from that, I know that they're not relatively prime. Right? Each of those things that we've been examining are things that you've seen in earlier class. So for the most part, that's the review. We care, of course, with algebra, we want to build on the algebraic skills, and that means we're going to start working with some variables. How would we get the greatest common factor between 16x squared and 26x squared y cubed? This is based on factorization. Whether you need to create a factor tree or you use the list method to figure out your greatest common factor, I would recognize that 16 is 2 times 2 times 2 times 2. X squared means that there are 2 of them, and then we've got y by itself. For 26, 26 is equal to 2 times 13. And then we have x squared, so there are 2 of them. Y cubed, so there are 3 of them. We're building upon our skill from before. We've already seen how to create the factorization of a monomial. Now we're adding another layer to it. What pieces do they have in common? They have a common 2. A common x, a common x, a common y. Each of those pieces are part of the greatest common factor. They have a 2, an x, an x, an x, and a y. That's our greatest common factor. A lot of times, though, we don't want to have the greatest common factor written out, expanded like this. Think about when we did our greatest common factor before. Did we leave the greatest common factor expanded? No, we multiplied it out and said it's 27. We want to do the same thing here. X times x times x. I'm sorry, I'd written down too many of them. There were only 2 x's in common. I wrote down 3. Yeah, don't let me get away with that. Okay, so they had 2 x's in common, 1 y in common, and so we have 2x squared y. This is the preferred format for the greatest common factor, where we actually do use the exponents. Would you like to see a pretty cool little trick here?
No.
The exponent on the x was a 2. The exponent was a 2. What's the smaller exponent?
2.
Well, they were the same, so we took 2. When we look at the y, we have an exponent, unwritten exponent of 1, an exponent of 3. Which one is smaller? 1 is smaller, and we wound up with a 1 for our greatest common factor. When you are looking for the greatest common factor, it's always going to take the smaller exponent. When the variable bases match, we will take the smaller exponent. That will allow us to identify these pieces much, much more quickly. For instance, what is the greatest common factor for the numbers 12 and 18?
6.
That has a greatest common factor of 6. When we look at the exponent portion then, we have an exponent of 3 and an exponent of 2 on those x's. take the smaller exponent. 2 is smaller than 3, so we have x squared, and we're done. We just need to take the smallest one. Doing the same thing, we'll look at the number 40 and 24. What is the greatest common factor for 40 and 24? Whether you use the list method or you use the prime factorization method, that's up to you. But you need to recognize that the greatest common factor is 8. Once you've got the number part, then we can move on to the variable part. Looking at the x's, what is the smaller exponent? 1. They're both an unwritten 1. So we've got an x in common. Then we'll look at the y variables, where we have y cubed and y. What is the smaller exponent? 1. And so we take the smaller exponent. That's our greatest common factor. We're done. Most of the work in identifying the greatest common factor of monomials actually comes from the number part. Because the variable part is nothing more than which number is smaller. That's easier than doing a factor tree. It's easier than creating a list. This, though, is the most important skill for us to take away. We did the factor tree, the relatively prime, all of those as things just to remind you what's going on with it. This is the primary skill. As I mentioned earlier when the video was paused, the reason we're doing this skill leads into factoring with the distributive property, and factoring with the distributive property is one of the major skills for Algebra 1. It is a significant skill that you continually use again and again through Algebra 2. It's a skill that does not go away in algebra. We will repeatedly need to identify the greatest common factor so that we can learn how to factor monomials and factor polynomials.